Very
Good
great.
afternoon. Good afternoon.
So, suppose I can share screen. Yeah.
You can. You are live now. You are live on YouTube.
Okay.
Yeah.
So, is the screen visible?
Yes. Good afternoon. It is visible. Good afternoon.
So I'll just stop sharing. So,
Ah.
start that. Suppose I can share screen. Yeah.
Yeah, you can share screen anytime. You are live
Okay,
now.
sure.
Live on YouTube.
I can share screen. So, is the screen visible?
Um, it's visible. It's visible on the YouTube also.
Okay.
Are you there? Yeah. Okay. I can see.
Yeah.
Okay. For a moment, I thought it's frozen, so I just
Oh,
wanted to.
no. The wife face was frozen, not the frame.
Tarun would be introducing you, and then you can start.
Sure. So, that would be like at
5 o'clock.
5 o'clock, right?
Yeah.
So, can I just go on mute?
Yeah, yeah. Even I'm going to go on mute and
Okay.
just give a blank screen. You can leave the. You can go to full screen mode so that the slide is visible. That will be great. Yes. Yeah. Test. Yeah. Good afternoon, Tarun.
Good afternoon.
Yeah, we are live on YouTube, and Professor Agrawal is there. He has set up the.
Okay, so I'll wait for another 11 minutes and then introduce himself and we can
Yeah.
get started.
Okay. So you're standing by. Test.
So good evening, all of you, and welcome to the COVID Week talk series. I have the pleasure to introduce today's speaker, Professor Manindra Agarwal. He is a BTech and PhD from IIT Kanpur from the Computer Science Department. His area of research includes computational number theory and cryptography. He has received many awards and recognition, and few notables being the Infosys Prize and the Padma Shri. And he is fellow of major national Indian academies in science and engineering. Today's topic is COVID Sutra, and I'll request the audience to please write down their questions in the question answer box and in the chat box. So after his seminar, we will take up the questions. So let's welcome Professor Manindra Agarwal for today's talk.
Thank you, Tarun. I hope I'm audible to everyone.
Yeah.
And, so this is the little bit of a play on the name of the model, the Sutra. So I'm going to describe the genesis of this model, and in general, starting with how the whole modeling effort started for pandemics, and what are the key aspects of our model, in what way does it differ from the previous models, and what are the predictions that come out of this model. So let me start with the point where this whole modeling story began, namely the Spanish flu of 1919. A very peculiar phenomenon. Well, data was probably for the first time getting collected properly, and this phenomenon was observed. This is a plot of deaths in UK. And one can see these three peaks, and the middle one is the largest one. It's very high and very narrow. So the question that arose was that, exactly what is the phenomenon that is causing this? This led Kermack and McKendrick in 1927 to propose the first mathematical model to track the pandemic progression. And what they did was quite simple, at the same time very elegant. They divided the population into three boxes. Susceptible are those who are not yet infected but may get infected in future. Infected are those who are currently infected. And removed are those who were infected in the past but are no longer infected. And this, notice, also includes those who unfortunately passed away. So the movement of people from these categories is very clear. Susceptible move to infected, and infected eventually move to remote. And what is key is they capture this movement of these people between different categories, and that will describe the dynamics of it. So let's do that. Let's use S of t, I of t, and R of t to represent the fractional sizes of these three boxes: susceptible, infected, and remote. And we achieve fractional sizes by dividing the numbers by the underlying population of the region we are studying. And that gives the S plus I plus R equals 1 as an invariant. Now let's move on to the movement from susceptible to infected. And let's estimate in one day how many susceptible people get infected. And here we are analyzing a large population. So we can look at the average behavior. And let's say a person meets k persons in one day. And when a person who is infected meets any other person, there is a certain probability of the transmission of infection to the other person. And let's say that probability is P, which is determined by really how fast does virus spreads, what is the medium through which it travels, and so many other factors. However, note that although a person meets k persons in one day, not all of them will come from the susceptible category. Some of them will be from infected category, and some of them will be from removed category. And neither of these two categories will get infected. We are assuming that those who are once removed, they remain immune to the infection. This is not always true, but this is the simplest assumption we can make to begin with. Now, so the question is, out of these K persons, how many are actually susceptible? Well, the answer is simple. Since S is the fraction of susceptible persons, so K times S is the estimate of the susceptible persons and infected person meets in one day. And each one of them gets infected with probability P. So one should expect that P times K times S persons get infected by one infected person in one day. And we denote P times K by parameter beta. So beta S persons are infected by one person in one day. Summing over all infected persons, which is that number is I times the population, we get that beta S I times population, many persons get infected in one day. And if we express this in fraction, dividing it by population, we get that beta Si fraction of population moves from susceptible to infected in one day. And that's what gives rise to this differential equation, ds by dt, susceptible always reduce, minus beta Si. This is the key or central equation of SIR model. The other moments are simpler to model. The ones that what fraction moves from infected to removed, that's dr by dt. That's how many new infected persons come to removed category in one day. That's going to be proportional to the size of infected category. The larger the size is, the more will move in one day to removed category. So we just make it some constant of proportionality gamma times I. And once we have these two, then change in I, di by dt, is just beta Si coming in every day and gamma I moving out every day, is the difference of the two. We can also model the mortalities. If we use d of t to denote the cumulative deaths at time t, which is going to be, of course, a subset of removed category. And the change in d, that is per day additional deaths, are also going to be proportional to the size of infected category. So some constant of proportionality eta times I. And this completely describes the dynamics of this model with three governing parameters, beta, gamma, and eta. So once we have an estimate of values of these three parameters, one can run the simulation and see how the model is behaving, what is the trajectory, and so on. How does one determine the values of these parameters? Well, beta, as we just observed, is like product of P times K. Now, P is a parameter that's dependent on the virus, the kind of virus it is, how fast does it spread, what medium does it use to spread, and so on. So that's can be estimated used by studying virus properties. Then K is actually a function of the population dynamics. What is the density of population? How much movement is there in that region? So that will impact the value K. Eta will be a function of the healthcare infrastructure. If the infrastructure is good, then the mortality rate will be less, otherwise higher. Gamma is also impacted by, again, primarily the virus properties, that for how many days on average does a person remain infected, and that determines gamma. So one has to study all of this to arrive at good estimates of beta, gamma, and eta. And then once we have the estimates, you can run the model. And the SIR model proponents, they did put in certain values of beta, gamma, and eta, ran the model, and they found that the dynamics projected is a good match to what actually happened. And from that time, this whole modeling effort started for various pandemics. Since then, SIR model has been built upon further for capturing the differing behavior of various pandemic. For example, okay, before I go that, let me just discuss one more important aspect which comes out of SIR model, which is quite a lot discussed these days also, which is the value R naught, which is connected to when the pandemic peaks. Its peak is when the number of infected cases are at their maximum. That is, I of t is maximized, which means di by dt is 0. And by this equation, we get that S should be equal to gamma or beta at that point. And that's beta or gamma is what the R naught value is defined to be. So when S is 1 over R naught, at that fraction of the population being susceptible, the infection reach their peak, and then the numbers start coming down. This also tells us that if R naught is less than equal to 1, that means S is greater than equal to 1 when the peak of infection happens. And S is always less than equal to 1. So that means that peak never occurs. And the pandemic really is not a pandemic, it's an endemic. It just keeps dying out. So estimation of R naught value is therefore also important, that they give a sense of how fast and how far will pandemic spread. So coming back to the other models that have been developed, SEIR is another model which brings in a fourth category called exposed, which models the situation when an infected person has a certain gestation period during which he or she is not infecting others, and after the gestation period, the infecting of others starts. So that's called exposed category, and this happens, for example, in measles. So susceptible move to exposed move to infected, infected move to removed. By the way, names of all these models, as you can see, are just the first letters of the various categories that exist. And the dynamics of it, again, can be described equally simply. We have now 4 values, S, E, I, and T. Their sum is always 1. ds by dt is minus beta Si, because only those in I infect, those in E don't infect. d by dt, well, beta Si comes in, and some fraction, alpha fraction of it goes out to infected. di by dt is alpha E comes in, gamma I goes to removed, and dr by dt is gamma I. And as one can readily see, if you add E and I, you just essentially get back the equations of SIR model. So SEIR, therefore, is a refinement of SIR. So is this another model called SAIR. This actually captures the pandemics where there are a number of asymptomatic cases, which means the virus initially, when it enters the body, the symptoms are not apparent, and after some days it becomes symptomatic, or sometimes it doesn't become symptomatic at all. So here the susceptible move to asymptomatic category first after getting infected. Some of them move to infected after some time, but some of them may just directly go to the removed category, and infected eventually go to the removed category. So this is SAIR model. The dynamics of it are also very equally easily described, except that now I have 2 removed subcategories, I should say, those coming from asymptomatic and those coming from infected. So I split that into 2, R sub A and R sub I. And sum of these 5 is now 1. ds by dt is minus beta A plus I, because both asymptomatic and symptomatic, they all infect others. And dA by dt, those we assume that initially everyone is asymptomatic. So beta S A plus I come in. Gamma A go directly to the removed category, and delta A go to the infected category. So the delta fraction at any point in time becomes symptomatic. And di by dt, therefore, is delta A minus gamma I going to the removed, and the rest is clear. Again, adding A and I and RA and RI essentially gives back the SIR equations. So this is the kind of models that have been in existence for a while. And some of them were used to understand the COVID dynamics as well. There are two major differences in COVID compared to the earlier pandemics. First is that there have been a very large number of asymptomatic cases, and most of them are not detected at all, but they continue passing infection to others. So this gives rise to a challenge that if you can't seriously underestimate the total number of cases, what can you do with that data? There is no clear answer to that provided by the earlier models. The second part, which is somewhat unique, is that because of the active controls applied to stop the spread of this pandemic, a population over which the pandemic is active has not been the entire population. It has increased over time, but the increase has not been very rapid. Earlier pandemics, one could assume that within a short time, the pandemic is active over the entire population of the region. Not so in the COVID-19 case, which gives rise to this additional complication that since we are talking in terms of fraction, the number of cases divided by population, then the population itself is now become a variable with time, because that should be the active population over which the pandemic is active. So how does one estimate this spread? That gives rise to another challenge. And in fact, there hasn't been a model that has looked at this aspect carefully. It can be modeled. One of the simplest ways, I should say, of modeling is the following: that you make the population dependent with time. So P of T is let's say, the population of that fraction of population of the population of that part of the population of the region over which the pandemic is active, or we say this population is within reach of the pandemic at time T, and define a new parameter rho, which is the ratio of P and P naught, where P naught is the total population of the region. So P naught captures the fraction of population over which the pandemic is active. And this parameter we call the reach of the pandemic. It is clear that reach starts somewhere close to 0 and slowly increases to eventually become close to 1. Okay, now coming back to first issue of what we sample is because of the large number of asymptomatic cases, not the reality. And then there are additional challenges added on top of it, which is like limitations on testing or underreporting, and that makes these numbers even more, let's say, further away from the reality. So one big question that has been raised in many places is, how much can we trust the reported numbers? Do they provide any useful information at all? And what I'm going to try to convince you is that they do, actually. Now, in order to do that, let me go back to SIR model and just do a simple calculation. Introducing a new terminology here, N sub I of T. This is the fraction of new infections at time T. We have already calculated that. That is beta SI. This is the new infection that get created at any point in time or any day. So N sub I is beta SI. Now S is 1 minus I plus R, you know. So we just rewrite this equation as I is equal to 1 over beta times Ni plus I plus R times I. So that's, if you look at it, it's an interesting equation in that there are 3 quantities. I is the active infections at any time, Ni is the new infection at that time. I plus R is the cumulative infections that have happened up to that time, and I, of course, is active. So these I plus R times I, Ni and I, they are linearly related as according to this equation. This also gives us a way of computing the value of beta. not by estimating through various analysis of population dynamics, virus behavior, and so on, but directly from data, provided, of course, we can estimate I, Ni, and I plus R. If we can estimate these three quantities, then parameter beta value can simply be computed through this. But of course, we know that we cannot estimate even one of these three quantities, leave aside all three of them, because we really don't know. In fact, not just in COVID, even earlier, although even assuming that everybody turns symptomatic, still there will be underreporting, and then getting a full estimate of this sizes remains a challenge. Even more so in the case of COVID, because as I've already said, that and everybody knows that the numbers that are reported are probably much less than the actual numbers. So let's give a name to what numbers are reported. So I'm going to define this terminology. N of T is the fraction of daily reported infections. This is a substitute for N sub I of T. That's the actual number of daily reported infections, and N of T is N sub I of T is actual number of daily infections or fraction of daily infections. N of T is just the reported part of it. Similarly, T of T is the part of I which is tested positive. So these are the known or detected active infections. And similarly, R sub T of T is the reported part of R. So those who have been removed and have been known to be positive earlier. So that's what connects R sub T to T. And what we know, the daily reported data, as you can see in, for example, COVID-19india.org, is actually, these are fractions. So just multiply them with effective population. T hat is rho P naught times T, T hat is rho P naught times RT, and N hat is rho P naught times N. These three quantities is what we know for every time instant, every single day. We have that. Now, if I just go back to I, R, and Ni, we saw there is a relationship between these three quantities. And but we measure only this T hat, RT hat, and N hat. So one can ask the question with some hope, is there some relationship between these three quantities? And here is a hypothesis, quite a strong hypothesis. So let's view it or look at it a little carefully. What the hypothesis is saying is that just as I, Ni, and I plus R times I had a linear relationship, T hat, N hat, T hat plus RT hat times T hat also have a linear relationship. The difference is that these constants in the relationship are probably going to be different. There it was 1, E was 1 here, and then B was 1 over beta. But in this case, these two quantities are going to be different. But that hypothesis is it really true? Well, fortunately, we can verify this because we know T hat, N hat, and T hat plus RT hat times T hat for every day. We can just plot and see if the linear relationship holds. In other words, we can also view it as every single day giving a three-dimensional point, one dimension on T hat, one on N hat, and one on this product. So you get a three-dimensional point in R cube. And what this is saying is that all the successive days points, if you plot, I'm going to put them on a three-dimensional space, they all lie on a plane. That seems a very unusual property or unlikely property to be true. So one can actually try verifying it. And instead of plotting in 3 dimension, I have plotted in 2 dimension by just taking a difference, T hat minus B N hat, for a suitable chosen value of B, and plotted it against this product. So this plot I'm going to show first for India. Here is the first plot. Time is 23rd March to 23rd April last day. These are the daily points. T minus Bn and T times T plus RT. The value of B is 3.86, E is about 39,000. And with these two values, these points are very nicely fitting on a line with the R square value of 0.99. There's a remarkably high R square value. So it's certainly capturing a very unusual phenomenon. And one has to assume that there must be something intrinsic property for which, because of which it is happening. It can't happen randomly. But we don't stop here. Let's move on in timeline, April 29th to June 20th. Look at these points. B and E value have changed. 6.38, 917, and R square is really very high. July 21st to August 21st. Again, B and E have changed. R square has remained very high. September 21st to November 1st. All very nicely lined up along a line. Very high R square. E has come down to 82. November 12th to December 31st. E has remained around 83. R square again very high. January 22 to January 31. This is just a 9 points here. R square very high. E is still around 83. But I just want to point out these 10 points. I just want to point out even 10 points, 10 three-dimensional points in R cube, all lying on a plane, is still a very unusual phenomenon. And March 22 to March 27, this is just 7 points, still very high R square value. E has come down a bit. And finally, April 27 to May 17, that's the last day I pulled out the data, all lined up beautifully on a line. E has come down to 38.6. So once you add up the entire timeline and see for how many points is this property holding, it turns out about 62% of days satisfy this relationship between the three quantities, but not all. In fact, these days can be divided into 8 phases. I just showed you 8 plots because for each phase has a different value of B and E. The question is, why is this happening, and is it something special to India? The answer is no. Well, at least the second question has an answer I can give immediately. We have simulated 26 countries, all states and UTs of India, and 200 plus districts of India. And each one of them exhibits the same property. A fairly good percentage of days satisfy that linear relationship, but not all. So the question then is that why is it happening? I just want to show you the Japan data, just to emphasize the point that it is nothing unique to India. Again, 19th February, 24th March, B 4.2, E is about 74,000, a very high R square. March 25 to June 2014, E has come down to about 6,800. Then June 20 to September 5, E has further come down to about 1,400. October 6 to October 21st. November 11th to November 25th, November 27th to December 10th, January 6th to February 10th, March 31st to May 17th. As you notice, he is successively coming down, becoming smaller and smaller. All the fits are exceptionally good. And this, for Japan, about 64% of days satisfy this linear relationship. And Japan has 10 different phases. Another observation is that for both India and Japan and everywhere else also, the value of E starts at very high level and then reduces rapidly, eventually settle down to something much smaller. So the big question here is, how does one explain this? What exactly is happening? Firstly, this linear relationship holding is very unusual for a large number of points. So why is this linear relationship holding? Second, what is being conveyed by this B and E values, especially E, which is varying very widely? And thirdly, there's still many days for which the relationship doesn't hold. So what does that mean? I mean, how does one explain the fact that a large fraction of days satisfy the equation, but there are days which don't? So all of these questions lead us to our model, the Sutra model. Let me describe the model now. The category diagram is very similar to SAIR model, except that meaning of some of the groups has changed. Susceptible remains the same. The next group is undetected. So these are infected people who are not detected. Many from undetected directly go to remote, but some test positive when they come to this category, and then eventually they all move to remote. So the first names of these categories are SUTR. So that gives the first 4 letters of our acronym, and we have added A at the end for approach. So let's see the dynamics of this. We have again the 5 variables, S, U, T, R, U, and RT. Their sum is always 1. ds by dt is minus beta SU. It's because all those who are tested positive, they get quarantined, and therefore they don't infect others. So it's only in U who infect others. So that many susceptible become infected every day. Du by dt has beta SU coming in from S, gamma U going out to RU, they go to remote, and then some X quantity goes to T, which I am not yet specifying. dt by dt is X coming in from U and gamma T going out to RT, and the rest is straightforward. Again, if you add UNT and RU and RT, you essentially get 2 SIR models. So this is also a refinement of SIR. Now, what about this quantity X? Well, in SAIR model, it was chosen to be some fraction of U. But this is not a good choice for COVID. And the argument is as follows. For COVID, the way infected people are detected is through contact tracing, mostly. And it happens in the following way. Somebody gets infected, develops symptoms, gets tested, turns out positive. Then everybody who got in touch with this person in the last few days is tested. Some of them are found positive. Then it may go on for further level, but at level 1 also it is true that for one infected person who is symptomatic and got tested positive, through contact tracing, we can find a few more who test positive. And everybody from contact tracing who was found positive got infected after this first person was infected, because the first person passed on infection to the others most of the time. So what it tells us is that those who test positive are likely to be recently infected than as compared to those who were infected a while ago. So what we should really do for X is take a fraction of those recently infected. Now the question is, how do we estimate the size of recently infected? Well, we do have beta SU is the most recently infected number. When one day, just the last day, beta SU got additionally infected. And in a few days' time, this new infected numbers don't change dramatically. So we can take the size of recently infected to be some constant times beta SU. And some fraction delta of that is X, and delta K we set to epsilon. And that's what we get as X equal to epsilon beta SU. And that's what we are going to use. As a byproduct of this choice, it turns out the analysis becomes very nice. Let me show you. Just look at the equations for u and t. You can, if I go back, du by dt plus gamma u is beta su minus x. And x is epsilon beta su. So this is just beta times 1 minus epsilon su. Similarly, dt by dt plus gamma t is beta epsilon su. So both look very similar. In fact, just taking epsilon hat to be epsilon over 1 minus epsilon, you just multiply this with epsilon hat and subtract from this. We get that t minus epsilon hat u's derivative is equal to minus gamma times t minus epsilon hat u. We know how to solve this. It gives us t is equal to epsilon hat u plus some constant times exponentially decaying function e to the minus gamma t. And this tells us that within a short time, this becomes negligible and t is roughly equal to epsilon hat u, making u converge to t by epsilon hat. This is a very nice and important observation because what it tells us is if we know, of course, know t, if we can estimate epsilon hat, which is same as epsilon, more or less, we can estimate u. Similarly, we get u plus ru by the same similar analysis as 1 over epsilon hat t plus rt plus some constant, and which tells us that ru quickly converges to rt over epsilon hat plus c. So again, if we can estimate epsilon hat and c, since we already know rt, we can estimate ru. And finally, we look at that number of new reported infections, n of t, that I had defined. So n is simply now x, which is epsilon beta su. And u, we use the fact that it converges to t over epsilon hat and substitute there. We get this. And for s, we replace, s is replaced by 1 minus all of this. And just simplify it. We get this equation. Convert it into the observed number, that is hats, by multiplying it with the population everywhere. We get t hat is equal to this constant times n hat plus this constant times t hat plus rt hat plus into t hat. And if we set this constant to be b and this part to be e, we get t hat equal b times n hat plus e over p naught t hat plus rt hat times t hat. And this shows that the relationship that I had hypothesized actually holds in the model. And this is the fundamental sutra of our model, exhibiting a linear relationship between 3 measurable quantities. And once we have this linear relationship between these measurable quantities, we can do many things. For example, but before that, let me first list out the parameters that we have in the model. We have beta, eta, and gamma carrying over from SIR model. Beta is contact rate. It governs how fast infection is spreading. Gamma is removal rate. It governs how fast people are getting removed. Eta is mortality rate. And then we have 3 new parameters. Epsilon, which is the ratio of detected to total infections. C is just a minor parameter. It connects RT to RU, and generally observed that C is very close to 0. So it can practically be ignored. And rho is the reach of the pandemic. This is also a very important parameter, measuring at what fraction of population is the pandemic active on. So now we can estimate the parameter values directly from data. We can estimate eta just by the death rate series, which can be done independently of everything else. So I'll not get into that too much. Gamma can also be estimated separately by the recovery data series. What we have is that daily new reported recoveries is gamma times t hat, which is daily active infections. So we have a whole time series of this available, And so the estimating of value of gamma is simply a method, just running the standard regression using linear regression using least square method. Similarly for eta. What is more interesting is estimation of B and E and other parameters. Well, we have this fundamental sutra, which is this linear relationship between these three quantities, which are measurable. And we can again use linear regression to estimate B and E. B is 1 over beta times 1 minus C. And as I said, C can be kind of taken to be 0. So B is really 1 over beta, which is like was there in earlier also. But anyway, so knowing B essentially tells us beta. And the knowing E is just tells us 1 over epsilon times rho. Again, ignoring 1 minus C factor here. So there's a product of epsilon and rho is what we can compute. And as already observed for India and Japan, these values change over time, both B and E. Why do they change over time? Well, B changes when beta changes, and E changes when either epsilon or rho change. In fact, that observation that E starts with very large and drops dramatically to eventually stabilize to something much smaller is readily explained here. Look at the formula for E. It has a rho in denominator. Rho initially, which is the reach of the pandemic, is to a very small fraction of population. So rho is very small initially, which makes E very large. And as rho increases, it brings E successively down and further down until rho stabilizes and then E also kind of stabilizes. So the model very nicely explains this observed phenomena of how the values of B and E are changing. And each such change we call as a phase change. So when a phase change happens, then the values of these parameters change. Why do phase changes happen? Well, beta reduces if there is a lockdown. If people become more conscious, they isolate themselves or wear masks. All of these bring down beta. On the other hand, crowding and more virulent mutants increase beta. Testing policies impact epsilon. If you are testing much more than and much more rigorously, then epsilon will go up. If you are testing less, epsilon will come down. Spread of infection to new areas increases. So increases rho. Rho measures the fraction of population over which the pandemic is active. So as pandemic goes into newer areas, or people who isolated themselves have come, therefore outside the reach of the pandemic, step into the crowd and come within the reach of the pandemic, that increases rho. So phase changes do occur. And what we assume here is that parameter values remain the same inside a phase and then change when the phase change happens. It's also reasonable to assume that when a phase change happens, the parameter values don't change overnight to the new values. There is a few days of drift, as we call it, when the parameter values slowly move to their new values and then stabilize new values. And this notion of drift also explains why for about 30% of days for both India and Japan, the equations were not holding, because that is a drift period for various phases. And the parameter values are drifting, and therefore equation naturally will not hold. And once they stabilize, the equation holds. So by observing all of this, we can actually not only observe find phase boundaries, we can also find for how long the drift is happening, and then find what is the stable values of parameters. All of this can be extracted from the reported data. But there is still more work to do, because we only know B and E. Even if we assume C to be 0, there is still 3 parameters here: beta, epsilon, and rho. How do we estimate these 3 parameters? So for that, the following is done. Let's define a function. So I'm taking now C to be a full-fledged parameter. Its domain and is this product of interval 0, 1 and interval -1 to 1, and range is also the same. So the first component is the range of values for rho, and the second component is the range of values for C. So the function f is defined as follows. On input, it receives as 2 numbers in this range. So R is a guess for rho and S is a guess for C. So you set rho to be R, C to be S. Once you set these two, then from this, knowing B and E, one can compute beta and epsilon also. That's straightforward. Once you know beta epsilon, we know all the parameters, and therefore we can compute the trajectory of the unknown quantities U and RU for the current phase. We can also compute the trajectory of T and RT, obviously, for the current phase. And we have this relationship that U plus RU is related to T plus RT via this linear relationship. So you plot T plus RT against U plus RU and estimate these two constants, which are the slope and the pentisa of this. This is a epsilon hat. A is epsilon hat, and S prime is just the constant C. So knowing this epsilon hat and C, you just compute the value of, again using D and E, the value of rho, which is this. And so output this quantity, that is the value of rho and C, which you computed through this mechanism. Now, what is true is if we had the correct input, that is the actual value of rho and C as input, then the output will also be the same value, because then this relationship for the same value will hold. And therefore, the correct value is going to be a fixed point of the function. Now, what we have experimentally observed is that this function f has a unique fixed point just about everywhere for all regions, for all phases. And further, that can be found very quickly by iterating f. Just take a random point, start on it, iterate f for 15 times, you arrive at the unique fixed point. Now, this means that if there is a fixed point is unique, then you know for sure that the fixed point is the correct value of C, and you can arrive at it very quickly by the second observation, thereby giving us all parameter values. Now, so what can we do with all this? Well, this is what the India parameter values look like. This is 9 phases. This is the first phase pre-lockdown that I had not shown earlier. I have starting date of each phase. The drift period is in the second column. The beta values are in the third column. So I just draw your attention to first to the beta values. Pre-lockdown, that is before 25th of March last year, the beta was 0.33. By the way, this plus minus range is this 95% confidence interval values. So this beta with 95% confidence lies in this range. So beta is 0.33. Then lockdown came, and the beta started going down, 0.26, 0.16. By April, it had 0.16. And then it remained at very low until October. In November, it started climbing up, 0.21, 0.22. This continued until beginning February. Then it started changing. But then there was a long drift period from 10th February until mid-March. There was a drift period. And then it stabilized to 0.39, a very significantly higher value. Then end of March, again, a drift period of 25 days. So that is by end of April, it stabilized to a somewhat smaller value of 0.33. So this very nicely corresponds. And remember, these are all computed plainly from the reported data, nothing else. But they correspond very nicely to what actually happened on ground. That lockdown reduced beta significantly. Then from November, this festival season started, beta went up. Then a new mutant hit here in sometime in February, March. Also, people became very careless. So that really made beta shoot up. Then in April, of course, things were controlled back somewhat. Some lockdowns were announced, and that brought the beta value down to 0.33. These are the mortality rates, so I'll just not bother about this. Let's look at the other parameters. Firstly, the gamma. We actually fixed gamma to be 0.1. And the reason for this is that virologists have studied the behavior of the COVID virus quite intensely and estimated that an infected person infects others for about 10 days. After that, infection may remain inside the person, but it is so low that the person doesn't infect others. So, whereas the reporting of recovery is when the infection goes away completely. So, there is slight mismatch in what is reported and what gamma should actually be. So, we have just therefore fixed gamma to be 0.1. And finally, let's come to the last two columns here, epsilon and rho. There is a caveat here. Caveat is the following. Our model can compute all parameter values except one, which is the epsilon value in the first phase. That is just at the beginning of the pandemic. What was the value of epsilon? That is something the model cannot compute from data and therefore requires as an external input, which we call calibrating the model. So I have calibrated this model at value 37. There are reasons to believe why this value is been chosen to be 37, but this certainly is not necessarily correct. So that's why the values which are shown in this column need to be taken with a pinch of salt. And this calibration also determines the values of rho. So exact values should also be taken with a pinch of salt. But what is still interesting is, doesn't matter what calibration is chosen, the behavior, the changes across the phases more or less get reflected identically. So the first observation here is that value of epsilon has hardly changed. It does change, although from the looks of it, it seems that it's fixed to 37, but actually it is not. So but it varies very little, 37.001, 37.005, and these are the kind of values you see. That's why you see only plus minus 0 here. So that's the first interesting observation. Second is, going to the last column, what one observe, again, not looking at the specific numbers as per se, but the change. The reach was very low until May, and then it expanded significantly in June and further expanded in July, August. And there is a very significant increase here. Again, this is purely from data, but this corroborates very well with the reality on ground, because this is the period when the reverse migration of workers happened, which took the pandemic virus to many parts of the country which were earlier not affected by it. Also, the lockdowns were relaxed from July onwards, so that also added to this expansion of the reach. And then reach pretty much remained stationary for an extended period, increased slightly here. But in the current phase, it has again shot up very, very significantly, again highlighting or pointing to the fact that a lot of people who were cautious earlier have dropped that guard. So these are the learnings one can see by looking at this parameter estimation. So one can, of course, that means this is a good way to explain the past, how things happen, why things happen. But we can also use it to predict at least the near future, because once we know the current parameter values of the current phase, we can extrapolate into future and see how the future will look like, and that should be more or less exact, provided there is no new phase that occurs. So this is what we have for the entire timeline for India. The blue curve here is the daily new infections that have been detected. And this is, we have just taken 7-day averages of everything, because just to smooth out weekly variations. And the orange curve is the one computed by the model using just the parameters I just described. The last computation was done on 29th April, somewhere here. And then the model predicted the peak to arrive at around 4th of May at this level, and then this should come down like this. In reality, the peak arrived a few days later on 8th of May, but the trajectory really is more or less identical that has been followed so far. In fact, this is 2 days old story. This is up to 17th May, but only on 18th and 19th data is also there, and that's also following this trajectory. But this is not only true for India. Here's Japan. Again, blue curve, the 7-day average of new infections. Orange curve is what is predicted by a model. Japan is currently undergoing their 4th wave, and our model predicts that we are really is at peak. This is the UP. This was updated on, last updated on 9th May, the prediction. And the reason for late update is that there was a phase change in UP towards the end of April because of the lockdown. And we have done an analysis of lockdown also. And if the lockdown was not there, what would have happened? And our estimate is that the number of new cases would have hit 70,000. Whereas now they just stabilize at around 35,000. And this is Kanpur. Last plotted on 6th of May. There was a phase change on in the beginning of end April, beginning May, same for the same reason of the lockdown. And the trajectory is captured like this. We have many more simulations at this website, sutra-india.in. So those interested may check out. All states and union territories of the country are done. About 200 districts are available, and we are planning to do all districts of the country. Now, finally, the future work. We need to incorporate in the model loss of immunity with time, because that's a well-established phenomenon. And that would need a regular serosurvey also to understand what the rate at which immunity is getting lost. Second, incorporate immunity induced by vaccination. Till now, vaccination level is low enough so that it doesn't impact the model much, but we have to incorporate it eventually. Third and fourth are more theoretical questions that what we have observed is that the function f that I had defined has a unique fixed point. But it will be very nice to actually prove that under certain reasonable conditions, function f indeed has a unique fixed point. And fourth is also a very important one, that we in a phase, whatever the current phase is, if we are in the stable phase of the phase, the parameters have stabilized, then we can predict the future reasonably well. But if we are in drift phase of a drift part of a phase, current phase, when the parameter values have not stabilized, they are changing every day, then estimating their stable values and predicting future is not easy at all. In fact, we cannot do as of now. The question is there some clever way, can one find one, to just look at the way parameter values are drifting and make a good estimate of where eventually will they stabilize? If that can be done, then the future predictions can be done even during the drifting phase, which is something that will be really useful. That's all I have. Thank you for listening, and I'll be happy to answer any questions that you have.
Thank you, Professor Agarwal. I have few questions. So there are multiple questions from Professor Somesh Mathur. So I'm going to elevate him so that he can ask directly.
Sure.
Because, there are a series of questions that he's asking.
Okay.
Professor Harish, can you elevate him to panelist? No. Somesh Mathur. Professor Mathur, you can unmute and ask the questions. Yeah, go ahead.
Thank you so much, Professor Gupta. My question to Professor Manindra is that this Sutra model is like the SEIR model with different compartments. Am I right in interpreting this? That it is like a nonlinear simultaneous differential equations that you're
Yes, very right. Mhm.
right. So this uses the time series data. Now,
That's right.
uh, if you use the time series data and if you establish relationship, it falls into that trap of all this autocorrelation and unit root, so that this R square value is very high. So you may establish relationship, but they may be spurious in nature. That's I mean, I'm just from econometric point of view. And second, these R0 that you calculate, uh, does it have uh, a lagged impact on the COVID cases? So as you had predicted in your model, that the R0 is falling, but the COVID case have a lagged impact. They may fall, but after some time. Or maybe COVID fatalities also have a lagged impact. And thank you so much, because solving this model, we had tried this, we had also published a paper, but solving it is really, really difficult. So thank you so much.
Yeah, that's all very interesting questions. So let me take them one by one. The first one is, whether the fit falls into, we get a high R square value, is it just a spurious fit? It's always possible it's a spurious fit, but here are the arguments against it. First, it is happening consistently everywhere. So when a phenomenon occurs, when there is a universal phenomenon that you observe, it's very unlikely to be just by chance. Second, with this, assuming this to be a correct phenomenon, and when we do the calculations of various parameters, there is a real, actual physical meaning to them, corroborating with what actually happened on ground. So that also adds weight to the point that what we are observing is actual reality, not something, or rather actual property of the pandemic, not something which just happened by chance. And second, regarding R0, we are not really calculating R0 directly. We don't report R0 value. We do report that when the peak is, do a projection when the peak is coming and so on. And so far, what we have observed is that there have been times when the predictions have been off mark. Punjab, we predicted a peak in beginning April, and it just kept going up and up. But for most of the time, I think our predictions have been
right. 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 Thank you.
So next is Professor Somnath Biswas. He'll ask this question. Please go ahead, sir.
Yeah, good talk, Manindra. Thanks. See, I just wanted to know this because this is also interesting. You say that beta is a product of K and
P.
K and P, and P is a property of the virus, and K is a property of societal conditions in that region. So, would you like to estimate these two separately? And I have another question. Then this is something bothering me. I mean, why should beta be less than 1? So these two. But let the second thing you can ignore. But the first two, it will be very interesting to get K and P estimating them.
Yeah, actually, that's a very good point. I hadn't thought about it, but I think there is a way to estimate. P one can estimate because it's a pure property of the virus. We can talk to virologists and they can tell us that, look, this
Sorry,
is what...
Manindra, can they? I mean, they found it. When they find a new mutant, they say, yes, it is a new mutant.
Yeah.
But the effectiveness, etc., I think it's very complex. But
Yeah, I know, but I think we have to rely on virologists because literally there is no way to separate K from P. It just comes in a composite package. It's just a product, and we only see beta. If we can find P, then of course we can find K, or if we can find K through some other means, we can find P. So maybe both approaches can be used. I mean, maybe talk to epidemiologists to do the mobility analysis to find, for at least for a region, what is value of K, and then use it to estimate P, and or vice versa.
Yeah. So in fact, they are saying that Punjab, etc., they have this British variant. This side, Maharashtra, it's the double mutant.
Yeah.
So suppose you assume two fixed values, something like that, trial, hit and trial, and something like that. Saying, because you have a lot of district data also, right?
Yeah.
And geographically, what I'm assuming is P should be kind of similar, contiguous regions. And K might vary between city and rural areas and all that. So in a way, you have a lot of data. If you get that data, I don't think that COVID-19 gives those data. But if you can convince
No, we can extract that data, at least for all beta values, I can extract for all districts and how beta values are changing.
Beta you can, yeah.
So that at least will tell us if assuming P is same for two neighboring districts, can show us how the, let's say, mobility is different.
Yeah, I'm saying that rural versus city, urban, because there the K is going to be different, right?
Yes, absolutely.
So that's what I'm saying, if you can do some separation. But that I don't think COVID data gives, right?
No,
COVID-19 doesn't give that. But ICMR has it. I mean, government has this data.
Well, ICMR is this very tough nut to crack, but we can try.
Okay, all the best. And thanks again. Yeah. Thank you, Tarun. Yeah,
thank you. Next is Professor S.N. Tripathi. He has a question.
Hi, Manind.
Hi.
Good talk, man. Yeah. So I have one question, is that the way you are modeling that the infection, right? The second, I think, part of your, let's say, the population balance equation, right? Whether that is factoring in this new phenomena, that is the airborne transmission, because as of now, you say that the person is in contact with someone, right? But in this case, one doesn't need to be in contact, and there are many such cases coming. And then they are saying that, well, indoor, the possibility is that there is one person and everyone, you can say that, is in contact with that person. Let's say there are 10 people in a room. But outdoor, if the virus is traveling, let's say up to 10 meters or so, that you can't say that that person has come in contact with someone. Now, is there a way to remodel that parameter which accounts for this transmission of the virus?
Yeah, I mean, there certainly is. One can create these further subcategories and have a different parameter associated with each one of them. That's possible. We haven't done it, but it is something that should be explored in future, definitely. Ours is a really basic model, and the one I think needs to build in somewhat more involved model, which can cater to different kind of dynamics for different regions or groups.
Gurunath?
Yeah, nice talk, Professor Agarwal. I just had two questions. One was that you tweeted earlier, and I just saw that tweet because somebody forwarded it to me, that you're trying to predict the second wave. Though in your modeling, I find that it has actually captured the second wave quite well. And it's even predicted the peak probably within an error of 2 days. So one was, why was that so? And if you can answer that question, I'll go for the second one, or you want me to ask the second question?
Let me answer this. So it's a very important question. So what I mentioned, if you recall, in a phase, the initial period is a drift period, and then there is a stable period. So when in the current phase, which started end of March, beginning April, initial 20 days were like drift period. And when we were in that period, our predictions were literally changing day by day because parameter values were not stable. So every day we calculate and we'll find a different parameter value and prediction will come out based on that. Around 20th of April was the thing when things stabilized. And on 25th April, I tweeted that new infection peak will be between 3.4 to 4.4 lakhs and will occur between 4th to 8th of May. And we stayed with that prediction from that because we knew that the parameter values are now stable. We could see that in the phase plot that all the points are lining up fine. And then we were confident that as long as things don't change now dramatically, this is what is going to be, and that's what it turned out.
Okay, my second question is that there are some things that the model fails to capture, and this is coming more from my knowledge of viruses. Like most of these microorganisms, like especially viruses, have typically a growth rate which we assume is the same for all mutants, which need not necessarily be so. In what I mean is that, let us say a mutant X infects an individual, you probably see the infection within say 5 days. Whereas a mutant Y might take 7 to 10 days or maybe longer because of the gestation period that it needs to cover within that individual. I think the model actually does not incorporate that. And the second issue I had was that I think you need to break down these two parameters which you are estimating, more so to incorporate the effect of governmental policy interventions to see if they're actually affecting them before stabilizing. When you had a 40-day lag period, it's like this. Supposing I impose a lockdown, did it take 7 days for the parameters to stabilize, or did it take 40 days to stabilize? And was it actually correlated to the events on the ground? And that might actually give a lot more information to policymakers so that they now know which direction to go. And this is my last question. Thank you.
Yeah. So thanks. The first point that you make is again similar to what Sachi made, and like I said, right now our model is a very, very simple model, and it certainly can be improved by bringing in more careful divisions, subdivisions, and interactions between them. But it just needs to be done carefully because it's easy to get kind of lost in complication. So, but if it's done well, it can certainly improve the model. Regarding the second point, again, that's an analysis that I am doing these days. I've done an analysis of the UP lockdown, and it comes out very clearly that we literally have dodged a bullet. The UP lockdown came towards the end of April. Had the lockdown not been there, and I actually tweeted that all this analysis, we would have hit a peak of 70,000 new infections per day, which doubles what we had actually made. And that would have been nightmare because even at 35,000 a day, everything was broken. With 70,000, you can just imagine the chaos it would have caused. So this lockdown in UP, I think, was a real lifesaver. And I've done this for Delhi. Delhi also really gave a good impact. As opposed to Telangana, I don't think Telangana really had that much of an impact. So one can various what-if scenarios through our model and compare what works, what doesn't work.
Okay, thank you.
Thank you. Next, we have Anshu Singh.
Yeah. Sir, your data analysis that you have done nationwide and also globally, I mean, a lot of people are talking about your data analysis. I have a very, very small question. Maybe it's a bit away from this data analysis. I mean, how do you infer it out the chances that this is not a bioweapon explosion of violence, but a natural?
From data, I cannot make out. I'm sorry. It is really, I think, biologists, virologists, or people experts in this domain People in our BSB department can perhaps comment more usefully on that. I just look at data, and from data, really impossible to infer.
Okay, thank you. So I read out one question from the chat box. How do you factor in vaccination and different variant of
So vaccination, as I mentioned, we have not yet incorporated in the model. We plan to do it next month when things like cool down a bit. And different variants, again, I showed that variants actually pop up as values of beta. The double mutant and the UK mutant all combined, the impact they had on India was, of course, and on top of it, people also becoming more mobile, was that beta jumped from 0.24 to 0.39. It's a more than a 50% increase. And that's how on these mutants and other things get reflected.
The next question is, how do testing policy and underreporting affect your parameters?
It directly impacts epsilon. The testing policy, because epsilon measures the fraction of the total infections which is reported. And so depending on testing policy, that value would change. So I should mention here just one key point that which is not, of course, the model shows it. I did not directly mention it. What the model shows is that what we observe, the reported data about infections, recoveries, etc., is a scaled down version of the reality. So you can say it's a toy version with a scaling factor of whatever appropriate one. So actual numbers are, of course, really different, but the patterns and the rise and fall more or less is in sync. So if the reported infections are rising, it indicates that actual infections are rising. If reported infections start falling, it indicates actual infections are falling.
Thank you. We have Dr. Ram Shankar. He has a question.
Yeah.
Please go ahead. Please unmute yourself.
So can you hear me?
Yes.
Yeah. So very nice talk. I have two very quick questions. In one of the slides, you mentioned the choice of epsilon value has to be fixed in the first phase. And then you also mentioned that, we have to take this value with a grain of salt. So my question is, suppose if you had not taken 37, if you had taken 25, how your overall outcome would have been affected? Would it be qualitatively same, and or it doesn't matter what value you choose, you will eventually arrive at the same conclusion?
See, the epsilon value is essentially, you can view it as a scaling factor with the reality. So what different epsilon value do is they change the reality. They don't change what is reported. So by choosing different calibration, the projected infection, the plots that I showed will not move an inch. They'll stay wherever they are. It is just that when you try to estimate what is the real number of infections, that is going to change by an appropriate multiplication factor. And so that is important when you try to estimate what percentage of population is currently immune.
So the actual number of affected population.
That's right. Yeah. So that is going to change by the calibration.
So my second question is related to the power of prediction. Although you said it's a simple model, and then there are talks about the third wave. Is it possible for your model to predict when this third wave will occur?
So as of now, no. The reason is that third wave will occur when. So firstly, we must realize that the second wave, by the time it is done, would have given natural immunity to a very large percentage of population of the country. There are some estimates which say it can even be as large as 50%. Now, unless that immunity wears off, there is hardly going to be a third wave. But that immunity is known to be around. Certainly survives for 3 months, but between 3 to 8 months, there is a significant drop. So until we model that in our model, we can't really predict the intensity of the wave correctly. In fact, that's what we had even in the second wave. See, we didn't know at what rate is the immunity is dropping. So we were still assuming that the immunity levels are whatever they were in, let's say, October, November. And that seemed to have, certainly was wrong guess. Because with that guess, we were saying that the second wave's peak will be similar to the first wave. We were off by a factor of.
Yeah. Thank you. Very nice presentation.
Thank you. Next, we have Vinamra to ask a question.
Yes, Vinamra.
Okay, she's typing on the chat box. Meanwhile, let me ask one more question. You showed 8 phases for India and 10 phases for Japan. Are these related to some clinical or, like, as you said, like reducing immunity level or something that we don't know yet? What is these phases are?
So phases are, like I said, we detect phases by simply when the equation breaks down. That's a phase change. When the equation breaks down, that linear relationship, we call it a phase change. Now, it's important to first, once you identify those phase changes, then it's important to go to the real situation, observe it, and see what do they correspond to. So, for example, India, phase 1 was pre-lockdown. Phase 2, it corroborates with starts of phase 2 essentially roughly coincide with the lockdown. Then, start of phase 3 coincides with a slight relaxation in lockdown. Then start of phase 4 coincides with further relaxation in lockdown in July. So that way you can see that the change in phases actually, certainly for India, actually corresponds to some significant ground level policy decisions or change in behavior of people or change in the mutation of the virus. Later on, for example, phase 8 and phase 9, phase 8 came because the virus had mutated and that caused increase in beta. So while the phase timelines are computed purely from data, what is good to realize is that what we learn from the data is actually, there is an actual physical understanding of that in terms of how the policy decision or things on ground changed.
Okay, thank you. So I'll read out Vinamra's question. She said, like, how small can we go with your model? I mean, you showed India, then UP and Kanpur. Can we bring it down to the level of our campus? Like,
no, that's not going to. It's not. So we need some numbers, frankly. So because a lot of this, see, at very small numbers, the errors become so large that there will be literally, because we do a lot of this least square estimation, and so that simply won't work. The numbers become too small. So I would say at least a lakh or so is probably what I think will be the minimum number on which the model can make some sensible predictions.
So are you also projecting uncertainty analysis for your model?
Yes, so I showed you in the phase phase table, all parameters we estimate with that interval of uncertainty of 95% confidence in. So that provides that uncertainty or the possible variations in the different trajectories.
So we thank you wholeheartedly and for such an insight into the model, and we hope that policies can be made with such robust data analysis so that a larger number of people can be protected. Thank you very much.
Thank you.
So tomorrow we will have Dr. Nadma Parveen talking to us. Please join us back.